Welcome to Dynamics. This is the introductory video lecture, and we're going to start with section 12.1. And just recall that statics is the study of equilibrium. And in statics, the sum of the forces equals zero, sum of the moments equals zero, which means that the body is either at rest or in constant steady motion, which means that acceleration is equal to zero. In dynamics, we're obviously studying things that move, and especially when acceleration is not equal to zero. So our equations that define our motion are sum of the forces equals mass times acceleration, and sum of the moments equals I alpha. We're going to talk about this equation in the latter half of the course. But in the first half of the course, we're going to be talking about particles and that are under forces and accelerations. We're going to start with Newton's second law. And Newton defined velocity as velocity is equal to the change in position with respect to time, or ds dt. And acceleration is dv dt, or the change in velocity with respect to time. So we're going to study these equations quite extensively. And first we're going to talk about particles and then rigid bodies. Particles are of negligible size and shape. This is often the appropriate assumption when the body is small compared to the surroundings, like an airplane in the sky, or when there's no rotation or no significant rotation of the body. Well, first we want to talk about rectilinear motion, which is motion in one dimension. So imagine a line here of one dimension, and first we need to talk about our position. The position is going to be where we are on the line. And if I'm here at position 0 or position 1 or position 2, you can see that I have both a magnitude, which is a length away from the origin, plus a direction. I could be positive away from the origin, or I could be negative away from the origin. Displacement is called the change in position, or that's defined as the change in position. So it is also a vector, meaning magnitude and direction. So if I've moved from here to here, even if I go through S, my total displacement is just S2 minus S0. So this is my total displacement if I've moved from here back to here. And we call that change in position. The average velocity then is going to be the change in position with however long it takes to get there. So that would be S2 minus S0. Instantaneously, however, I will have a different velocity, and that velocity may be whatever it is that whatever speed I am at that particular time. The speed is defined as the total distance traveled over however time that takes, and the total distance traveled meant that I went this distance and then I went that distance, and so that total distance would be the total distance traveled, and we use the absolute value for that. Speed is going to be a scalar because it doesn't care whether I'm going in the positive direction or the negative direction. Acceleration is going to be the change in velocity over time, and so that would be v2 minus v0 over the change in time. Okay, so we're going to start with Newton's equations. And Newton defined the velocity and acceleration, as we talked about on the first page, as a is equal to dv dt, and v is equal to ds dt. Now these can be manipulated algebraically. In other words, I can set this one equal to dt, and I can set this one equal to dt. Then I set those equal to each other, and then I can combine these two equations, and I can get this second equation, or this third equation. AdS is equal to v dv. Now, what I'm going to say here is these are the three primary forms of Newton's equations, and they can be used to integrate and take derivatives in a variety of ways, and we'll find that quite useful. So let's take a quick example here. Let's say that if my position is equal to 5t squared, and if I want to find the velocity, I say the velocity is equal to ds dt, which is equal to is going to be d dt of 5t squared. Now I can take, since 5t squared is a function of time, I can easily take the derivative of that, so that would be 10t. I can find the acceleration is equal to dv dt, and if v is a function of time, which indeed it is, I can take the derivative of that, so d dt of 10t, and that's equal to 10. So we're going to get lots of practice with taking these derivatives. All right, an example I'd like to share with you is, let's suggest that velocity is expressed as a function of time, and we want to find expressions for acceleration and position. So let's say that v is equal to 2t. meters per second. We know that a is equal to dv dt, which is equal to the time derivative of velocity. Velocity is given as a function of time. Take that derivative, we can see that acceleration is now going to be 2, which is a constant. If we want to find position, let's say that v is equal to ds dt. That can be manipulated to ds is equal to v dt, bringing that dt over onto that side with the v. Now we say that ds is equal to v dt, and the integral of ds is equal to the integral of v dt, where v is equal to 2t, so we have the integral of 2t dt. We can integrate both sides. Now when we take integrals, we know that it's always necessary to evaluate, or conditions are always necessary to evaluate integrals. Unless otherwise specified, assume that t0 is equal to 0. In other words, time begins at 0. However, velocity, acceleration, and position may not be 0 at time is equal to 0. So you need to watch for what these guys are at whatever time they're defined at is in the problem. But a time will always begin at 0. And we can use either a definite integral or an indefinite integral approach when evaluating these things. So let's do the indefinite integral first. We're going to say that the integral of ds is equal to the integral of 2t dt. Integrating both sides, we can see that s is equal to 2t squared over 2 plus a constant. Simplified as s is equal to t squared plus a constant. Same with over here in a definite integral. A definite integral means we have limits on the integrals. And again, time always goes from 0 to t. Distance could be from whatever the position is at time 0 up to the position that we're looking for. The integral of ds is equal to s minus s0. Over here we got 2t squared evaluated from 0 to t. Evaluating that, we got s is equal to s0 plus t squared. Now you can see that these equations are essentially the same. Here I have a constant, which we have to evaluate, but here I have position 0, which I don't know until I know my conditions. So both forms are valid, and we have to evaluate these two unknowns with the conditions that are given. So for example, if the position of 0, or of s was equal to 0 at time is equal to 0, we plug that into this equation. We can solve for the constant is equal to 0, so s is equal to t squared. The same thing over here. If s is equal to 0 at t is equal to 0, I can find position 0 is equal to 0 and find s is equal to t squared. Okay, and if you have something just a little more difficult then, let's say that position is equal to 6 at time is equal to 2. Well, we plug those guys into this equation. We can solve for the constant, which is going to equal to 2. Then our final equation would be s plus t squared, or s is equal to t squared plus 2. Same thing had happened on this side. Plugging 6 into position and t is equal to t squared, I can find that s0 is equal to 2, and I can get the same equation. So comfortingly, everything is the same when we're done evaluating. So it really doesn't matter if you choose the indefinite integral approach or the definite integral approach. I find it generally is easier to use the definite integral approach, and where we evaluate with defined limits. So that's what we'll use most of the time. Okay, here's another very common example of acceleration and motion, and that's the constant acceleration special condition. And gravity is one of those conditions where acceleration does not change. And there are a lot of other conditions that we'll see. Often vehicles under braking will be a constant deceleration, or maybe sometimes when you have vehicles under constant acceleration if you mash on the gas. These are the three equations that we will be using for constant acceleration, and those are given by integrating these three equations in this manner. And you can walk through the math if you wish, but the main thing to take away is these three equations, and those should be committed to memory or to your note sheet. All right, so let's go through a little example then of a constant acceleration problem. Let's say that this bus starts from rest with a constant acceleration of 1 meter per second, and we want to find the time required for it to attain a speed of 25 meters per second and the distance it traveled during that time. So let's try the time first. Here's our equation that we can use. It's constant acceleration, so I can use v is equal to v sub 0 plus at. I was given acceleration. I said it started from rest, so that v0 is equal to 0. I ended up with a constant velocity of 25. Solving for time, I get that equal to 25 seconds. The distance it takes, we can find that out with either of the other two remaining equations. But let's say that we'll use this one first. This is the distance we're looking for. We know that it starts from 0 with a velocity of equal to 0. I know that now that it takes 25 seconds, so I plug 1/2 AT squared, and I can see that it takes 312 meters to get, or he travels 312 meters during that 25 seconds. We can also use the velocity equation where we say v sub 0, or v squared is equal to v sub 0 squared plus 2as. We know our acceleration, we know, and this is the distance we're looking for, is the distance there, and we know it ended up with 25 meters per second. So again, we get the same answer, which is good. Okay, next thing is we've talked about velocity and accelerations as function of time. However, they are often expressed and behave as functions of either position or velocity. So in other words, we will consider velocity as a function of position, acceleration as a function of velocity, and acceleration as functions of position. For example, let's say that we have velocity as a function of position here, and here's a little equation. We're going to say velocity is equal to 2 plus 0.2s. Over here we can manipulate this, or we have this equation which can be manipulated into this form. So AdS is equal to v dv. Bringing the ds over onto this side, I can say acceleration is equal to the velocity times dv ds. Alright, so since velocity is a function of s, I can use this equation in this form. So let's say that a is equal to the velocity, which is 2 plus 0.2s. And then dv ds is equal to, since velocity is a function of x, I can take the derivative of this equation. So the derivative of 2 is a constant, so that's 0. The derivative of 0.2s is just going to be 0.2. So I've multiplied that whole thing by 0.2, and I can see that acceleration is 0.4 plus 0.04s. Now we see that acceleration is a function of s. We may want to put this into the time domain, and we note that by saying v is equal to ds dt. Taking the dt over that side, the v under there, we see dt is equal to ds over v. And if I do that, I can integrate both sides, and I can say time goes from 0 to t. And over here, I've got the integral of ds over v, which is 2 plus 0.2s. Now, and this would go from 0 to s. How do I know from 0 to s? I guess I have to look back up here at my initial conditions, which I didn't highlight. But let's say our initial conditions are that s is equal to 0 and v is equal to 0 when t is equal to 0. And if I do that, I can go from s, or integrate this side from 0 to s. Now, how do I integrate this? In the back of our book, we have a variety of integral and derivative forms, which you should become familiar with. And if you look at the form for this one, you can see that this is of the form, or this is evaluated as, on this side, I guess I got t. On this side, I got 1 over 0.2, the log of 2 plus 0.2s, evaluated from 0 to s. So this right here is this integral evaluated. All right, now how do I find some times, or how do I find some values? If I solve this now for time, I'm going to say that this is 5 times the log of, evaluating this side, I get this is the log of 2 plus 0.2s minus the log of just 2 when s is equal to 0, and so I get that. And if I want to find out position, now as a function of time, I need to solve this equation for position. Doing that, I evaluate that, I bring it over to that side of the equation, and divide by 5, and I take the e to the both sides, and well, I guess I got it right there, and then I can see that 5e to the quantity 0.2t plus the log of 2 minus 2 is equal to position. So again, this is kind of a long drawn out thing, but we need to become familiar with how we can move in the time domain, or move from the time domain into the s domain or velocity domain and back to the time domain, because sometimes that will be of advantage to us. Okay. Sometimes velocity and acceleration are related, and that acceleration can often be a function of velocity. And again, this is probably well, it is very common. I'm not going to say it's the most common alternative scenario, but we find often that velocity is, or acceleration is, a function of velocity. So here's an example: a is equal to 20 over v squared, and we'll say our initial conditions are v is equal to 0, t is equal to 0. And I can say that a is equal to dv dt. I can set this equal to dt, which is dv over a. And then I bring that over here, so dt is equal to dv over a, which is 20 over v squared. Simplifying that, I get v squared dv over 20. Now that's pretty easy to integrate. Now I can integrate both sides here, and I can say that this goes from 0 to t, so that's just t. This one would go from 0 to v, so that's v squared over so that'd be v cubed over 3, and the 20 is still there, so that's v cubed over 30. So I now have velocity as a function of time when I simplify that. So that's kind of nice. I can, once I have this t is equal to v cubed there, I can just bring the 60 times there and take the cube root, and I get velocity as a function of time. If I want to find acceleration now as a function of time, since I can take a is equal to dv dt, so that's equal to, bring that 1/3 over there, I got 60t on the inside, and then it'd be 1/3 minus 1, so that would be raised to the minus 2/3. But then I still have to take the inside derivative, so that'd be 60. Evaluating that, I get this is equal to a. So 20 over 60t to the 2/3 is equal to acceleration. Now, did I do this right? Let's check our work real quickly and evaluate this at t is equal to 10 seconds and see if I get the same answer. So if I take velocity right here at 10 seconds, so I'm going to say 60 times 10, so that's 600 to the 1/3, I get velocity is equal to 8.434. Plugging that into this equation, or not, then I could also put 10 seconds into this equation and find out what my acceleration is. So 20 over 600 to the 2/3 is equal to 0.281. Using either one of these things and going back up to my original equation, I can check my work here. So here if I put a is equal to 20 over v squared, and if I have v is equal to 8.434, at 20 over v squared, I can check that acceleration is equal to 0.281. So I got the same answer using both techniques, so I'm convinced then that I did my math correctly.